next topic about complexity, geometry, and generalization in deep neural networks.
Cool, thanks. Yeah, so I'm a lover of AIT, but also a bit of a skeptic of AIT. I tend to think more in terms of like finite circuits and maybe not like completely recursively enumerable measures of complexity. So let's talk about it. Okay, so I showed this GIF at the last symposium, and I'm showing it again because it's my favorite GIF. So I found this on Twitter a few years ago. If you take a video of cream pouring into coffee, and you just zoom in on the mixing, and you compress it with JPEG, and you plot the file size over time, what you find is when it's just black coffee, it's very compressible. When it's mixing and getting some tendrils, the JPEG file size goes up, and it reaches some point of maximum complexity. And then it starts to go down again. And in the end, you just get this brown cup of coffee. So I really like this. It's an open system. There's a question of like, what scale should we examine the system at? Like, what is the notion of coarse graining? Why does this happen? What's going on? So this has kind of driven a lot of my research, is just finding this one GIF. So I think neural nets go through some kind of complexity phase transition when they're learning patterns. Cool. Okay, so I guess one of the fundamental questions in machine learning, or in deep learning right now at least, is why do neural networks generalize? So why is it that some networks get zero training error and they don't generalize well, and other networks get zero training error and they do generalize really well? How can we explain this phenomenon? So we have some like kind of classical theorems from statistics about what we expect to cause generalization. And it's supposed to be something to do with model complexity. So this is the bias variance trade-off. Hopefully you all know it, but the idea is if we have a model that's too simple to fit our data, it won't even like fit the training data very well. And so the generalization error will just be dominated by a training error. Like it didn't even fit the training data. On the other hand, we can have models that are way too complex. So here, what I want you to imagine is like some 100-degree polynomial trying to fit some linear data with a little bit of noise. It's like way overfitting. So the training error will be zero. It's perfectly fitting the training data, but it's not going to generalize well. It overfit. And so we're supposed to want to be in the middle here. You can formalize this with these generalization bounds. So there's all kinds of these. We'll talk about a few of them. But in general, they look like this. There's the test error is bounded by the train error plus some measure of model complexity. And you almost get to choose your own measure of model complexity. Okay. And what we're supposed to believe, or at least what some sloppy labs have published, is the bias variance trade-off is wrong. Neural networks are secretly different from everything else. Mathematical theorems are not actually true. So what we're supposed to believe is this is the bias variance trade-off. So what I'm showing here is both the train and the test error for a network, and I'm growing the size of the network, and I'm training it to convergence. I'm training it for a very long time. Okay, and so what we see is as you make the network bigger, the training error goes down. That's good. That's what's supposed to happen. Your deep learning framework is not broken. And then this is supposed to be the bias variance trade-off, where we made our model more complex, it fit better. We reached kind of some optimum point, and then we started making it big, and it's getting worse again, it's overfitting. And I guess sort of the surprising thing was finding, well, if you just keep scaling the networks up, there's another turnaround. And then it starts to go down monotonically again, and we don't overfit, actually. And you can just keep making it bigger forever and just get monotonic improvement. So we're supposed to believe, like, if model size is the same thing as model complexity, this doesn't make sense, according to bias variance trade-off. So we need to like refine our intuition of the difference between the size of a model and its complexity. And also, please feel free to ask me questions along the way. I prefer if it's more casual. Okay. Any questions so far? Yeah.
You said some groups are saying math wrong. What are they disagreeing with? So you said some groups are
so if you go look at like the OpenAI double descent paper, they're sort of like
they're saying this
they're saying that this is they're kind of define some crazy notion of complexity, which is just the size of the network. And then they're like, oh, look, this breaks the bias variance trade-off. Like neural networks are very magical. So go read the original OpenAI double descent paper. Okay, so that's in model size, this kind of phase transition of generalization, you could call it if you want. I've also studied this phenomenon called grokking, which happens instead of over size, it happens over training time. So what's going on? So we're training a network longer and longer and longer. This is on a log scale. What do we see? The training error just goes down, and the test error actually goes up, stays high for a very long time, and then it suddenly generalizes. So this is kind of a nice phenomenon. If you just look at the accuracy rather than the loss, you're kind of like instantly getting 100% accuracy on the training data. And then much later, you suddenly get 100% accuracy on the test. So this is going to be a nice model system for us to understand the complexity of the system over time. Okay. Okay, so what is complexity? I guess everyone here has a shared opinion, but there's lots of notions of complexity. So classically, machine learning researchers were studying these notions of complexity, which I would kind of call like the function class expressivity. So this is like, you have this class of models, how many of the exponentially many functions that there are can you actually represent? That's roughly what these measure. These are not dynamical. This is like fixed. Once you've defined your network, it's just fixed. So these cannot possibly explain, for example, the grokking dynamics. Okay. Then there's the ones that the machine learning practitioners actually use. So if you go like to an organization that trains neural networks, they're going to be monitoring things like the L2 norm of the parameters or the L1 norm. If they're a little fancier, they'll do something like the curvature of the loss landscape. I'm glad Alessandro is here, so he can comment in later. Yeah, so these are kind of geometric quantities on the parameter space. Okay, so on the parameter space. But you might see already like, okay, what does the parameter space matter? It's all about the function. It's all about the function. The function is what causes the generalization, not the parameters. Okay. And then the one that we all like, of course, is these kinds of notions of the information in the network. So this could be like the Shannon coding rate or the Kolmogorov complexity. So we're going to talk about the relationship between these quantities and try to get a little more better understanding of generalization. Okay. So it's weird. The geometric quantities, like they do seem to kind of correlate. Like it does seem like if you track L2 norms, sometimes it really does tell you things. But on the other hand, there's this kind of very basic argument that it's not even wrong. It can't possibly explain anything because of these reparameterization symmetries in the network. Okay, so what do I mean by that? So imagine like a very simple two-layer ReLU network. So I just have like matrix times input, ReLU, matrix times input. Okay. If I scale up the first layer by alpha, and alpha is a positive real number, and I scale down the second layer by alpha inverse, I'm going to leave the function invariant. So the function is not going to change, but I'm going to change the parameter scale arbitrarily. Okay, so I can mess with the parameter scale as much as I want without changing the function at all. So it seems like this notion of like generalization from these geometric measures in the parameter space like don't really make any sense at all. So can they possibly explain generalization? Maybe not. And yet empirically, they do seem to correlate. I ran a Twitter poll and I asked people, does parameter norm correlate with generalization? And people said yes. And then I asked them, does the curvature of the loss landscape correlate with generalization? And they said no. This is funny to me. Okay. So, okay, let's review the information theoretic ones, although I guess for this audience, not as relevant. Yeah, I mean, maybe we just skip it, but we can at least recall, like, what is the classical notion of complexity, like from Shannon information? He's basically identifying it with the entropy of the distribution. Okay, we should skip this. Skip all of this. Okay, but Shannon tells us to think about like the distributions of things. So like, what is our distribution over weights, for example? But in general, we don't know the true distribution, and so we can't compute its entropy. But there is a nice measure, the KL divergence, which tells us the excess information needed to code samples from one distribution using another distribution. This is also called the relative entropy. And the reason I bring up the KL divergence is it has this really nice property. It's reparameterization invariant. So once you define it, it's just this fixed geometric thing in the parameter space. Doesn't matter how I change what my axes mean. The KL divergence is invariant. So this is going to be a nice quantity to use to get around that symmetry problem. Okay. And what is the interpretation? Okay, I didn't really explain this to you, but just think of the KL divergence as the description length in the unit of bits of our model Q under our prior P. So there's a new problem now, which is like, what should the prior be? What should the prior be over your neural net parameters? I mean, obviously we all just init with like some kind of Gaussian or something. So maybe that's our prior. Maybe we need a better universal prior or something like this. Or maybe we need to define a prior in function space and then pull it back into the parameter space. I don't really know. So we're going to start with our prior, and then we're going to kind of train our network weights. And we want to end up with some posterior, some like shrunken distribution around where SGD took us. And then the KL divergence between those two is going to tell us how much information is actually in the network, or at least it's going to be an upper bound. Yeah, any questions on that? It's probably a mix of. Okay. This is your chance to ask about KL divergence. Okay. All right. So that's like a little bit of the information theory. So how does this relate to generalization? So there are these packed phase bounds. Again, I'm not really going to like explain how they're derived. It's kind of just inverting a Hefting inequality. But what do they say? So that what they say is this is the generalization error. In statistics, we use like the risk term. The generalization error of our posterior, so this is that final distribution that we're putting on the weights, is bounded by the empirical risk. So this is the expected training error under that distribution, plus this is called the complexity term. And so here we're going to use the KL divergence, and that's going to be reparameterization invariant. So I'm just saying such bounds exist, and they look like what I showed you at the beginning of the talk, which is something like test error is bounded by train error plus model complexity. Here's the model complexity. And remember, the model complexity is measuring how much information is in our Q relative to our prior P, which is subjective because the prior is subjective. Okay. Skip. Okay. So we want to try to measure the amount of information in the network. And our intuition is, when it's overfitting, when it's not generalizing well, it's kind of just memorizing all the data. And so that measure of information in the weights would probably be large. And then when it's generalizing, maybe we expect it's somehow actually compressed all of that data. It's not just acting like some giant lookup table. It's like forming a theory of the thing or finding some patterns in it, and it's representing the simpler pattern. So what we'd really like to show is, I think it would be quite intuitive to see like, okay, the information content is really high here and really low here, and it goes through this like compression dynamically during training. So that's some work I did a few years ago. So I didn't use that exact setup there, but so here's train accuracy, here's test accuracy. I used some other methods. Let's not get into it. But if you measure the file size of the network after you compress it in some clever way, you do find this rise and fall of complexity. So it's like you can actually measure like the networks are memorizing when they're overfitting, and then when they generalize, there is this like fall of the information content. Yeah.
Yeah, just looking at that, when you call phase transition, so kind of it's trying to figure out what the problem is, then it figures it out. Jumps. So, but does that jump? Presumably it depends on whether the problem is actually fundamentally easy.
Yes.
Not easy, but like, oh yeah, now I've got it.
Yeah.
Once that you reach your moment. But
exactly. So it needs the problem to have much lower complexity than the network.
Okay.
Yeah. So I guess you might not expect this, like maybe in language modeling, like it does seem like they are just memorizing a bunch of things, right? I mean, people have done all these studies where like you can get verbatim, like long text passages out of the language models. So clearly they are memorizing. So maybe we're like actually wasting most of the capacity of these large models just memorizing things. Yeah.
I've always imagined that they sort of do both. They first
Yeah.
memorize,
Yeah.
and then on top of that, they
Absolutely.
Magic.
Absolutely.
But if the complexity drops, they should forget in this case, right? They should forget all the stuff they've memorized. Is there something special?
Yeah, I didn't like do any kind of like empirical like proving that they've forgotten.
Okay.
Yeah, but that would be interesting.
Well,
That's cool. So this is modular arithmetic. So the grokking tasks are just train a over-parameterized transformer to do x plus y mod p.
Yeah.
Yeah.
But I'm just confused why they would. Yeah, unless there's some kind of regularization.
There's regularization.
Okay,
Yeah, there's
so
weight
then
decay.
based-
So here there's like I threw the kitchen sink of regularization at it.
Okay.
Yeah,
so
yeah,
then
yeah.
Once you've dropped, then you can forget everything. Oh.
Mm.
Yeah, then I
Yeah, so probably the picture I'd have in mind is like so you're on this like you're in your parameter space and like the loss gradients are like aggressively pushing you towards the thing that like immediately works the fastest, which I guess is just memorizing. Now you're on that like train loss equals 0 submanifold of the parameter space. And now you're going to stay on that manifold because the loss gradients are going to keep you on it, but the regularizer is going to push you around. And it's probably going to take you to a place that generalizes. And so that's what's going on.
That one way in which you can see it is you're turning the stochastic in the center, which basically makes it a diffusion process with the drifter. So you have the force of gradient in the center is pushing you in some direction, and then you have the noise, which is just trying to make you diffuse. So now you can use just the standard results from diffusion theory, which would have that there is a phase transition where the force of the drift stops being strong enough to oppose to the diffusion term, and then you basically stop moving and you just expand the resolution. It's both ways you're in. And to prove that this is actually what's going to happen, you can characterize qualitatively when the transition happens based on the amount of noise you're adding, and the amount of noise you're adding depends on the learning rate and the batch size. So you can check that in those plots, the point of the transition as you change the learning rate and batch size moves exactly like predicted by diffusion theory based on the ratio between learning rate and batch size. So I would say it's pretty established at this point that that is the main behavior driving that kind of stuff. And then that is the connection you have with information, and because the noise of SGD is exactly what is destroying the information contained in the weight. So
He was mostly directing that at you.
The memory, the weights, or I can just press the number, like the switching from memorizing individual sample to more sort of chaotic way. Memorize knowledge is important memory.
Okay, wait, let's talk about this outline. Did you have a question?
I was gonna say, I think the same thing as that.
Okay, cool. Okay, great. Yeah, so I think the Grokking case is nice. That's clear. I think the hard part has been to show that a similar thing is happening in double descent. So there, like the models are getting bigger, and like, is your compression method actually good enough to show that the largest models, which are generalizing best, are actually simpler and have less information in them? It's like a non-trivial task. So hints of what's coming, hints. Okay, so a lot of this depends on, if we want to measure the information in the networks relative to the prior, we need a really good posterior. We need a really, really good posterior. So what should we use? Well, if we put on our physics hat, let's just do everything to second order, and everything's a simple harmonic oscillator. And all I know how to do is Taylor expansions. Okay, so we're going to use the Hessian. So what is the Hessian? The Hessian tells you the local curvature in the loss landscape. So we're gonna put a posterior on our weights locally according to the Hessian curvature. So in some dimensions, it's gonna say, I can perturb this parameter a lot without changing the loss too much. So I can put a really wide posterior in that direction. So we call those flat directions. But in some directions, the loss is going to be super sensitive to that parameter getting perturbed at all. Okay, so we have to put a very sharp posterior. So we have to pay a lot of information to specify these parameters very precisely, but we get a lot of information back by specifying these parameters very insensitively. Still, it's in parameter space, which is kind of not that nice. And I think we need to go beyond that. And I think Andrew Wilson has a nice paper on this like 2 weeks ago. So this is all probably out of date. Yeah, Hessians. Okay. And what do we know about Hessian spectra? So there's some good empirical work. This is Tong et al. 2025, actually showing that basically universally in all deep neural networks, if you like spend the compute and compute the actual Hessians, you find that they're power law distributed. Okay, so that's interesting. So what is that telling us? Like, there's a few parameters that really matter a lot, and then there's kind of this long tail, but it's continuous, so it's kind of scale free. Like, where should you be? What's the maybe the bulk of this is kind of telling you, or the decay rate is telling you the complexity of your model. So if this decays faster, your model is simpler. Only a few parameters really explain all of the loss locally. Whereas if it's super flat, then you need a lot of parameters to explain everything. So yeah, I haven't looked at this. I actually should. Like maybe in the memorizing models, you're going to find very flat eigenvalue decays. Okay, sorry, Alessandro. Okay, so here's the setup of how we're going to measure the information. So we're going to have this information Lagrangian, which is giving a Pareto trade-off between the risk and the complexity. Then we claim under a Gaussian prior, the Gaussian posterior, so the Laplace approximation that minimizes the information in the weights is this one. So maybe we can do a little bit of arithmetic. So if our eigenvalue is small, so if we're in this like flat dimension, this is going to be 0. And then our sigma q is just going back to the identity. So it's becoming really wide. It's going back to the prior scale here. Whereas if h is very large, that's going to dominate. This part doesn't matter. And so we're going to have large number inverse. So that's going to be small. So our covariance is going to be very narrow. So just to walk you through the arithmetic there. So super simple. Okay. Then, I mean, this is all like very simple stuff, but if you measure the KL divergence between two Gaussians, this is what you get. Don't bother with it too much, but what I do want to point out is, look, there's something like an L2 norm. This is what the machine learning practitioners are using. And then you have your curvature term, or log curvature. So these things that people have like empirically picked up on that they find correlates with generalization, like do actually show up in the expansion. The cool part is, each of these depends on parameterization. With the KL divergence, we already know is invariant. So actually, this whole thing is invariant. So even though there's parameterization dependence individually, the total thing is invariant, which is cute. Yeah?
Sorry, I'm slightly lost on. So I understand that Q is this posterior, this curvature posterior.
Yeah.
What are you comparing against? P?
We're just putting a Gaussian prior centered at 0 with some like, it's isotropic even. I mean, this is like literally the stupidest thing you could possibly do.
The way in which we justify that was how many bits of information do you need to encode the weights? You don't need to encode that exactly the floating point of which you weights because you perturb them a little bit so fine. So how much can you perturb the weights? It depends on the curvature of the loss landscape. You can perturb more if that's flutter. So instead of having a fixed quantization scheme, the same way quantization is basically the same as putting a stochastic distribution over the weights. So let's put a Gaussian distribution over the weights. Let's put any prior, you can take uniform, it's going to be improper, or put a very like flat Gaussian as prior. Then the amount of bits I need to send to someone else to encode the weights, if they agree that I'm going to encode them as Gaussian, is the KL divergence between my Gaussian and the prior Gaussian, which is that expression over there.
So it's basically information gain between your prior and your posterior.
It's
Yes.
many bits of information I need to send to transmit my weights.
No, it's exactly what you said.
Okay.
So yeah, just in terms of the cuteness of like, okay, it's reparameterization invariant, so that's nice. But these metric quantities show up, so it's like, oh, maybe that's why people kind of picked up on that. And like there probably is some kind of symmetry breaking in the learning process, right? Like the learning process is not parameterization invariant. It's clearly strongly dependent on it. Anyway, okay. So you can do this sort of like Hessian-based posterior and like plot some generalization bounds. So here I'm showing the test error over time in a grokking setup, and then you do actually have this like generalization bound that's tracking it. So that's nice, but we already kind of knew grokking was doing that. So the cool new thing is kind of explaining double descent a little bit better. Yeah. So often what people do is like optimize the bounds. Like you have this generalization bound, you have like a way of computing it. Okay, let's like find the thing that minimizes the bound. But there's always going to be this trade-off between the implied complexity of the model and the empirical risk. So what's the setup? We're going to find the posterior Q, which minimizes that complexity, the KL divergence, such that the training risk under Q, the difference between the training risk under Q and the training risk of my like golden SGD weights is bounded by epsilon. So I'm going to control the trade-off between complexity and predictive performance with this epsilon term. Okay. Now I can send epsilon to 0, and what does that mean? I'm resolving the model at different levels of its like predictive detail. So what does this look like? So this is fun. Okay, so first of all, just this is a double descent setup. So here I'm plotting the complexity of the model, and here's the model size increasing. And you do actually find the medium-sized models which overfit the most are the ones with the most information in the weights, and the larger models have less information in the weights. So that's already, I think, very cute. Is like, actually, the largest models could be compressing the best. They're able to learn the most compressed description. And if you have a really sensitive measure of the information in the weights, the largest models are maybe the simplest ones. So that's nice. There's a decoupling of complexity and scale. Yeah, sorry, I just said that. Okay, and so what is this crazy GIF? So what I'm doing here is changing epsilon. So that's the resolution on the predictive performance. And what you see is when epsilon's large, like here, the apparent complexity of the model just monotonically increases with scale. But when you shrink epsilon, so you're examining the model at this finer and finer level of predictive detail, that's when you find that rise and fall of complexity. So you actually only observe this effect when you force the predictive performance of the models to be very good. But I like this as a way of kind of like scaling into the models and looking at the information at different length scales. Okay, I need to go a little bit faster, but so as I said, there's kind of always this trade-off between the apparent complexity of the model and like the distortion, the excess error on the training data. That's this term. So we can examine that trade-off by varying beta. So which scale is the right one? So let's just look at the whole rate distortion curve. So here's again model complexity on the y-axis and this log of the distortion term on the x-axis. And yeah, you find a power law because neural networks, everything's a power law. So that's fun. That's fun. And what you can then do, sorry, I don't have enough time, but you can get the slope of the power law. So again, that's kind of that like spectral decay rate. And that's actually quite predictive of generalization performance. Yeah. And so now, apologies for the spotting, but if you plot that spectral exponent, you find that it correlates pretty well with that double descent phenomenon. Okay. Yeah. Okay. So what have I shown here? I think a more rigorous demonstration that larger models actually can learn simpler hypotheses by showing the information in the largest models in double descent is actually less than the smaller models. And I think we're kind of able to better unify grokking and double descent under this like kind of clean information theoretic framework. And maybe we can get some new angles into like generalization phenomena and potentially scaling laws with this rate distortion function. So there's lots of deep connections. If anyone's into like the neural tangent kernel, sort of that whole like all those Harvard physics guys, I think this is kind of like a dual picture. Yeah, so that's my talk. Thank you.